So we're going to prove something about something that doesn't seem very related to what we've done so recently, but we're going to use basically the triangle removal lemma to prove this. So let me give you a definition first. So a three-term arithmetic progression, which I'll often just refer to as a 3AP because it's way too long to keep writing three-term arithmetic progression. It's basically just three numbers where the gap between the smallest and the next one is equal to where the gaps are the same, right? So kind of three numbers of the form. So you've got A, let's say A plus D, and A plus 2D. So yeah, you've got where let's just say that where D is at least 0. I mean, you could allow to shift to the negative direction, but you may as well just not, right? Obviously, in the special case where D is 0, it's like kind of a trivial arithmetic progression. It's just like A. So we say it's trivial. We say it is trivial if D is 0. And otherwise, it's a non-trivial three-term arithmetic progression. So there's a famous theorem of Roth. From I think the 50s or something like that, which says that basically if I have a subset of the first n integers that doesn't have a 3AP, then it must be quite a sparse set. So for any delta greater than 0, there exists some n naught of delta such that if little n is at least, so I'm using a capital N naught here, so if little n is at least n naught, and A has no non-trivial, A is a subset of 1 up to n, which has no non-trivial 3AP, then the size of A is at most delta n. So yeah, this should say A is a subset of 1 up to n with no 3AP. Okay, so basically if n is really large, at some point the set with the biggest set without a 3AP will go below like 1% of n, like 1 up to n, and then at some point it'll go below 1% of 1% and so on, right? It's you cannot have a very dense subset of this of 1 up to n that has no 3AP, no non-trivial 3AP. Okay. Questions about that statement? Okay, so how we're going to prove this is using the this Ruzha-Semeretti theorem. Well, I maybe won't restate the whole theorem, but so let's just dive into this proof, and then I'll remind you what we're using. So what I'll start by doing is let epsilon be delta over 81. there's going to be some 9s in this proof somewhere, so 81 is going to show up because of that. And then we're going to let our n naught of delta, so it's going to be, so little n naught epsilon 1, where this comes from this root, so over 9, where this is from the this Ruja. So I'll remind you what this means, but this Ruja-Semeretti thing. So the way that this n naught is defined is that, like, if yeah, so if G, so the way, so just to say what is this number, it has the property that if G is a graph with n, at least n naught epsilon 1 vertices, where each edge is in at most one triangle. So the 1 here corresponds to this one. Last time we did a more general result where you had an L here. But yeah, we're just going to need the 1 with a 1. So then G has at most epsilon n squared triangles. Okay, so that just explains what is this number, right? Okay, so these are just some parameters. And oh yeah, let's let A be a subset of n. Have, you know, let's let this A have no non-trivial 3AP. And our goal is to show that the size of A is less than or equal to delta n, right? Okay. So yeah, somehow I want to construct a graph where basically the triangles in this graph somehow correspond to 3 APs or something. And then I can like apply this, you know, this kind of statement here. So here's how we're going to construct the graph. I'm going to take 3 sets, x, y, and z. Okay. Let's label the vertices of x by little x 0, you know, little x 1, up to x little x 3n. There's a reason why we're going to go up to 3n, but it's, I mean, it's not super important, but okay, now we're going to go y0 in y, so y1 up to y3n, and then z0, z1 up to z3n. So we're going to call this graph, let's say, G sub A. So, because this is going to be a graph that depends on the set A in some way. So far we haven't defined the edges, but yeah. Okay. So here's how I define edges. So all the edges are going to go from x to y, or x to z, or y to z, right? And the rule is xi is adjacent to yj if j minus I is an element of A. So for edges between here and here, xi, yj is an edge of GA if and only if j minus I is an element of A. Yeah.
Have we defined where we're getting, like, what values the, like, xi's are yet? Or, like, are those elements of A?
These are not like numbers or anything. These are vertices of the.
Sorry.
The indices of these things are going to kind of correspond to, well, I mean they are natural numbers. So the sort of the indices of xi, y, yeah. All we care about is that they're indices. Yeah. So yeah, these are just kind of abstract vertices at the moment, and then we're going to kind of define what it means for them to be adjacent. So if I've got an edge here from xi to yj, what that means is that j minus I is in A. Okay. Then we're going to have a similar thing between y and z. So let's say yj zk is an edge if and only if k minus j is in A. And then for the last edges, it's going to be a little bit different. Kind of because, in some sense, what we're trying to do is encode something like, if I take a 3AP, like I've got a distance of d here, and d here, and like 2d here. So there's some kind of thing going on like that. So I want my third condition to be a little bit different than the other two. So let's say xi zk is an edge. It turns out the right thing to do is to say, I make this an edge if and only if k minus I over 2 is in A. Okay. So of course, sometimes k minus I will be odd, and then it definitely cannot be in A. But that's not an issue. I mean, so yeah, this condition can only hold when this is even and this fraction ends up being an A, right? So the edge condition's clear. So if you had the A, you could construct this G, right? Okay. So I want to somehow use this magical property about triangles. So I want to show that this GA satisfies this condition that every edge is in at most one triangle. And then I can use that to get that there are not too many triangles, right? And somehow that's going to correspond to bounding the size of A, but we'll see that at the end. So let's show that every edge of GA is in at most one triangle. Every edge of GA, is in at most one triangle. So okay, if I have an edge, if it's in no triangles, I don't really care about it. I mean, that satisfies the condition. So we may as well start by saying, let's look at a triangle, and let's look at the edges in that triangle and show that they can't be in any other triangles. So let's start with a triangle and show. Because if we start with an arbitrary edge, if it's not even in a triangle, there's nothing to say about it. I mean, it satisfies the condition. So let's just suppose xi, yj ZK is a triangle. And we're kind of going to simultaneously show that the edge xi, yj, yj, zk, and all three of these edges they're all in this triangle, and they're not going to be in any other triangles. Okay. So now we interpret this statement in terms of the edge conditions on the graph, right? So this means that, so therefore, j minus I is in A. Also, k minus j is in A, because that's the condition on edges between here and then here. And then we know that k minus I over 2 is in A. Okay. So let me make sure I get these the right way around. So now I'm going to just say, okay, list these numbers in the correct order. So if I take j minus I, then look at the number k minus I over 2, and then look at k minus j. Now, by looking at these, it's not clear that this, to me, it's not clear that this is an arithmetic progression, but actually it is. So this is a 3AP where the common difference, so like the difference between these two and these two, the common difference, so like the D in the definition, is I minus 2j plus k over 2. So what I mean by that is if I take this number, j minus I, and I add this, it'll give you k minus I over 2. And then if I take that number and I add this, it'll give me k minus j. But I mean, oh, by the way, this is a 3AP in A, right? Because all three of these numbers are in A, right? So what can I say about this? I mean, A is not supposed to have any non-trivial 3APs, so but in some sense, A does have 3APs, right? If you take just the same number 3 times. So basically this common difference is 0, right? That's the only, if this was a triangle, if this thing is non-zero, then that means I found a non-trivial 3AP in A. So this just has to be 0. So since A has no 3AP, then for every triangle like this, we must have that this common difference, so I'll just take the numerator. So I minus 2j plus k equals 0. But that simultaneously will tell you that, like, each of these edges is going to be a unique triangle, because if I know I and j, it uniquely determines k by this equation. If I know I and k, it uniquely determines j. So yeah, any of the indices. So therefore, any of the indices, I, j, or k, is uniquely determined by the other two. Okay, so each edge is definitely in at most one triangle. So each edge because yeah, we started with a triangle and said there can't be another one. Is that clear? Or okay, so by the definition of like my n naught and the fact by this Rougier-Semiretti theorem, yeah, this graph we can bound the number of triangles in GA. I mean, so. So let's note that, I mean, first of all, how many vertices does GA have? It's like, I think it's 9n plus 3, which is, because of how I chose the, so, which is going to be bigger than my n naught of epsilon 1, since n is at least n naught of delta, which we define to be n naught epsilon 1 over 9. So you've got like an extra 3 here, right? Yeah, so therefore this Rougier-Semiretti thing applies. So GA has at most epsilon times the number of vertices of GA, which is 9n plus 3 squared triangles. Okay. Which we can remember what epsilon is. It's delta over 81. This is where the 81 is coming in. I've got like a 9 squared, right? 9n plus 3 squared, which I'm going to throw away a little, I mean, not very much, but a slight bit, and just bound this by, let's call it delta n plus 1. I think this bound is correct. If it's not, make epsilon a little smaller, and then, I mean, like if I change this to 81,000, then you're probably going to be safe here, right? But yeah, I think this is probably correct. But the key idea is basically I'm canceling the 9 squared with the 81, and then like kind of replacing with an n plus 1, right? But yeah, if you prefer, make this a lot bigger, and then it's definitely going to be true. Okay, so we've got an upper bound on the number of triangles. Now I'm going to get a lower bound, and it's going to give me the bound. Basically, I've got a delta n here. So if I can get a lower bound on the number of triangles in terms of A, that might be useful for getting the upper bound on A. So yeah, let's lower bound the number of triangles. So here's how I'll get a lower bound. So for each A in A, and let's say R in 0 up to n, where was I looking? Look at the triple XR, Y R plus A, and Z R plus 2A. So I claim this is a triangle in GA. Why? Because, well, if I look at these indices, the difference between them is A, which is in A. The difference between these two indices is also A, little a, right, which is in A. And if I take the difference here divided by 2, it's also equal to little a, so it's also in A. So if you think about it, how many distinct triangles do we get? I mean, for each little a and each R, this is giving us a different triangle, right? If I change the r value, then it changes which xr I'm choosing, for example. And yeah, so yeah, this is definitely giving you different triangles for every choice here and every choice here. So GA has at least size of A times n plus 1 triangles. Okay. But we already upper bounded the number of triangles. So if I combine those two things together, I get that the size of A times n plus 1 is less than delta n times n plus 1. Cancel the n plus 1s. The size of A is less than delta n, which is what we wanted to. It's even a little bit better than what we wanted to prove. We just wanted the, yeah, so it's even a strict inequality. So yeah, this is just combining with the bound on the number of triangles that's behind these boards, right? It was at most that. Okay. And this is, so this proves this Roth's theorem, which is like a pretty famous result in additive combinatorics. I have to say, this is not the original proof. Actually, the original proof of Roth's theorem, it's really quite beautiful and it gives you a lot of intuition. I kind of feel like this proof is, it gives, to me, it gives me no intuition. It's just magic that happens because of the regularity lemma. But it does kind of show the power of this approach that we can prove these kind of somewhat deep results by just applying the regularity lemma, basically. I should also say the first kind of application, maybe not of the regularity lemma itself, but of ideas related to it, was to prove what's known as Samaretti's theorem, which is very similar to Roth's theorem, except you're looking at k-term arithmetic progressions. So if you have a set that doesn't have a 100-term arithmetic progression, it must be sparse. So we're not going to prove that because it's a lot more involved, but yeah, that's also somehow related to regularity. Okay, one thing we haven't done is we haven't proved the regularity lemma. So that's going to be basically the focus for the rest of this week. So what I'd like to start by doing is just giving you kind of a high-level overview of how this proof is going to go. Okay. So proving the Samaretti regularity lemma. And yeah, we won't give the proof today, but we'll just start getting the ideas. So someone gives you a graph, right? And you want to produce a partition with these nice epsilon regular properties and whatnot, right? So yeah, so kind of my input is a G, and I want to output a partition which has like 3 special properties. Well, okay, and I guess there's some kind of T and an epsilon. So yeah, the number of parts has to be at least T, and at most some constant involving depending on epsilon and T. I want most of the pairs to be epsilon regular, except for an epsilon proportion of them, and I want all the parts to be about the same size, right? Okay, so what I'm going to do is, so we want the number of parts we want k to be at least t. There's some integer t floating around here. What I'm going to do is just start with a partition, an arbitrary partition into t parts, and then we're going to refine it and refine it. So if I started with t parts, well, then it's going to have t at least t at the end. So kind of start with an arbitrary partition. Let's say P0 into T sets of size. I'll just write approximately, n over T. N is the number of vertices. And when I say this, I really mean floor or ceiling. But yeah, basically it's like n over T, right? Okay. So obviously, if we're doing this in a totally arbitrary way, we're not going to satisfy the conditions of the lemma yet. I mean, that would be quite lucky. But obviously, if it does satisfy the conditions, we would just output this partition, right? So now here's the idea. So if it doesn't satisfy the conditions, so what we know is that, essentially what we know is that this partition is not a very good approximation of our graph. So if it does not satisfy the conditions, then that must mean there's a lot of pairs. So, okay, it does satisfy most conditions. It does have the condition that the number of parts is t, which is between t and some whatever. It does have the property that all the parts are the same size. So the only property that can fail is that there must be lots of pairs, too many pairs that are not epsilon regular. So what does that mean? It means, so for example, if this pair is not epsilon regular, compute the density of edges between those two parts. Let's say it's a half, okay? What does it mean for it not to be epsilon regular? There's some significant size set here, of at least epsilon proportion of the whole set. And there's another one over here where the density between these things differs substantially from the density between the actual parts. So let's say, I don't know, the density between the parts is a half, but between these two things, it's like, I don't know, 3/4, right? So that's kind of telling you that our partition so far is not a good approximation of the graph, because there's this kind of dense part here that's not being represented well by just saying, like between these two parts, we're just saying it's kind of density a half, but actually between these sets, it's like 3/4. So this is kind of a bad approximation. Okay. So our goal is to expose the structure of the graph, right? There's this hidden dense thing here that is not well approximated by saying the density between these things is a half. So I want to pull that out and be able to see it, which just kind of means, one thing you can think is, well, just refine this partition to make these things kind of new parts of the partition. Right? And that will kind of show the density between those two things. It's not quite what we're going to do, though, but it's something like that. So essentially what we're going to do is we start with an arbitrary partition. We're going to keep refining it and refining it to get a better partition that shows more of the structure of the graph. And we want to show that this kind of terminates after a finite number of steps. And then we'll be happy. To do this, though, it's a little bit fiddly to say why it would terminate. But there's turns out there's a convenient way of doing this. So basically what we're going to do is we're going to define a sort of quantity that measures how good a partition is, how good it is in terms of epsilon regularity. And basically, if we can show that the goodness of a partition goes up every time we do this refining step, and if we show that the goodness of a partition cannot exceed a certain value, if it keeps going up, then at some point you're going to have to terminate because it can't go above that certain value. So let me give you a definition. So the mean square density of a partition P of, let's say P is like x1 up to xs or something, or maybe T, let's call it T, of the vertices is defined to be, so the notation we're going to use is just f of P, not very inventive notation for a function, but and what this is equal to is the sum over all I and j in like 1 up to t squared, where I is not equal to j. And then I take the density between xi and xj squared times xi, size of xi, the size of xj, I believe divided by n squared. Okay. This may look kind of arbitrary, but here are the kind of magical properties. So it turns out you can prove this number is always between 0 and 1. Okay. If I've defined it properly. And here's the thing. What we're going to show is that if let's just think about the first partition P0. If this doesn't satisfy the criteria of the theorem, then there exists a refinement of P0 into at most, so P0 had T partition classes, and now we're going to have at most T times 2 to the T partition classes, or maybe 2 to the T minus 1. It's not, I mean, that's not going to make a big difference, but let's just say at most 2, to be safe, T times 2 to the T classes. Such that okay, I'd like to have a name for this refinement. Let's call it Q1. So sorry, a refinement Q1 of P0. There's a reason I've changed from P to Q. We'll see in a second. But such that the mean square density of Q1 is at least the mean square density of P0 plus epsilon to the 5 over 2. So the idea is if your partition is good, just output it. If it's not good, refine it, and you can boost the mean square density. By a number, we can actually, like this is this is not decaying as I do this. I mean, this is just a number, right? So in some sense, if I did this enough times, it can't go above 1, so it must stop. And at that point, you must have a thing that satisfies the criteria. There is a slight issue with this Q, though. So I'm going to take this P, I refine it to get a Q, and this Q may not have parts of the same size. So a problem is that the partition classes of Q1 will all be different sizes. So we kind of lost that property. But also, there's a way to, so by, so there's a second step here. We refine P naught to get Q1, and then I refine Q1 and reorganize it to get things of the same, parts of the same size in a way that I don't lose too much. So by refining and reorganizing, so we'll say, I mean, this will be a technical thing we'll do next time at some point. Q1, we get a partition P1 such that the mean square density of P1 is at least what we had for Q1 minus, let's say, epsilon to the 5/4. And the classes of P1 all have roughly the same size. Up to taking floors and ceilings. Okay. So basically, we boost the mean square density. We then reorganize to make the parts the same size. We lose a little bit in the mean square density, but the amount we boosted is more than the amount we lost. So in total, from going from P0 to P1, we're going to have epsilon to the 5/4 higher mean square density. And so therefore, doing this 1 over epsilon to the 5/4 times, because this cannot go above 1, you'll eventually terminate at a partition that must satisfy the criteria. Otherwise, you'd go above 1, right? Okay. As a sort of outline of how this might work, does this make any sense? Any questions about this? I'm not saying here, so there's also some dependency on how many parts P1 has in terms of Q1. I can't remember how it works, so we'll have to work that out when we get to it. But yeah, basically, we started with T parts. We go T to the T. And then maybe P1 will have a few more parts than Q1. But it's still going to be bounded in terms of this parameter T. And then if we think of repeating this and repeating this and repeating this, still the number of parts is going to depend on, each step is going to depend on T. And the number of steps that you do this depends on epsilon, because it's 1 over epsilon to the 5/4. So in total, the number of parts at the end is just a function of epsilon and T, right? Okay. Maybe let's talk a little bit about how to make this Q1, because this kind of connects to what I was kind of trying to say over here. And yeah, so you'd now get a Q2 from P1 and then a P2 from Q2 and so on and so forth. And so let's kind of think about a natural way of getting this partition Q1. So suppose I've got my P0 partition. Now, this was an arbitrary partition. At this point, it could be the case that maybe every single pair fails to be epsilon regular. I mean, we have no control over that. This was an arbitrary partition. In the worst case, maybe every single pair will fail. So yeah, for each pair, if it's not epsilon regular, take a certificate for that, meaning a set here and a set here that have the wrong density between them. So it doesn't match the global density. So there's a deviation of at least epsilon between the density between these things and the whole parts. So this is like a certificate showing this pair is not epsilon regular. Of course, if a pair is epsilon regular, then you don't need a certificate. There is no certificate, so just don't do anything. But like, so I kind of find this certificate. Maybe this pair is not epsilon regular, so I can find another set and another set, right? And maybe this pair is not epsilon regular, so there's a set here and a set here. And you can do that between all the other pairs, right? And you can see, what is this making? It's kind of making like a Venn diagram sort of thing. Like if there are t parts here, there may be, just looking at this part to the other parts, there will be like t minus 1 possible, up to t minus 1, it could be fewer, certificates, which will break this into, it'll break this into 2 of the t minus 1 regions. At most, right? It could be fewer, but you see what I mean by looking at the kind of intersection pattern of all the different certificates. So this here, it's like broken into 8 regions, right? But if I had another part here, it could split all of these regions in half, right? And that's sort of why we're going to go from t parts to t times 2 to the t minus 1. So I was right when I wrote the minus 1. Because that's all we're going to do. We're going to say we take all the certificates that show it's not epsilon regular, and my Q1 will just be all of these regions of the kind of Venn diagram in all of the different parts. Okay, so it's going to, in this case, it would boost the number of parts by a factor of 8, which is like, if the number of parts is 4, then that's 2 to the t minus 1. But generally, it's going to, every part becomes like 2 to the t minus 1 parts. Okay? But of course, like I said, there's no way that these are all going to be the same size, right? So there is legitimately going to be tiny ones and big ones. And that's why we have to, once we find Q1, we have to sort of clean it up to get everything the same size. And then we just repeat that, right? So the tricky part is going to be showing that this actually does boost the mean square density by a measurable amount, right? By some epsilon to the 5 over 2. But yeah, we'll do that next time. Any questions about this high-level overview, though?